Hey, what do you think a plane flying through a crosswind, a swimmer trying to cross a river, and, I don't know, an apple falling from a tree all have in common? It might seem random, but they're all described by this sort of hidden language that governs the physical world. And today, we're going to decode that language. We're talking about vectors.
So let's start with something really simple. Think about it. When you push something, what information do you actually need? It's not just how hard you push, right? That's only half the story. You also need to know which way you're pushing. And that simple two-part idea? That's the foundation of every single vector.
Okay, let's take this airplane. The pilot is trying to fly straight ahead, but there's a strong wind coming from the side, pushing it off course. Well, a vector is the perfect way to describe that wind, because it captures both its strength and its exact direction. It tells the whole story.
Or what about a swimmer who's trying to get to the other side of a river? They have their own force, pushing them forward. But at the same time, the river has its own force, the current, pushing them downstream. We can actually use two different vectors to show both of these forces working at the exact same time. And then, of course, there's the big one, the most universal force of all, gravity. It's this constant pull, always directed straight down towards the center of the Earth. And that pull has a very specific strength and a very specific direction. So all of these things, the wind, the swimmer's effort, the river's current, and gravity, these are all just real-world examples of vectors in action.
So, we've seen how vectors can describe these different forces. But, an arrow is just a drawing. To really get what a vector is, we need to break it down. We need to deconstruct its two essential parts.
And here it is, the official definition. A vector is just a quantity that has both a direction and a magnitude. That's it. The arrow we draw is just a handy way to represent those two pieces of information. So the crucial point here is you absolutely cannot have a vector without both of those things. It's a package deal. Let's look a little closer at those two parts. First up, magnitude. That's really just a fancy word for the strength or the size of the vector. How strong is the push? We show it with the length of the arrow. So a longer arrow means a bigger magnitude. Simple. And the second part is direction. This one's pretty straightforward. It's just which way the arrow is pointing, which we can measure as an angle.
Now this brings us to a really common point of confusion. We see coordinates on a graph all the time, and it's easy to mistake them for vectors, but they are fundamentally different things. And believe me, understanding this difference is key.
So yeah, let's just ask the question directly. If you have a point at location 3, 4 and a vector written as 3, 4, what's the big deal? I mean, they look almost the same, right? Parentheses versus brackets, but they're telling us completely different stories.
Okay, the difference is simple, but it's also kind of profound. A point with its parentheses is just a static location. It's a pin on a map. You could say it's a destination. But a vector with its fancy brackets isn't a location at all. It's a set of instructions. It says, go this far in this direction. So get this, it's not the destination, it's the journey. And you can start that journey from literally anywhere. All right, that's enough theory. Let's apply everything we've just learned to a single, concrete example that brings all these forces together. Let's picture a father pulling his daughter on a sled up a snowy hill. The scene itself is really simple, right? But the physics happening here are fascinating. And to really see what's going on, we can draw what's called a force diagram. It's basically just a collection of all the different vector arrows that are acting on one object. In this case, the daughter on the sled.
Let's build this thing out step by step. First, you've got gravity. It always pulls straight down. But obviously the sled can't just fall through the hill, so that force gets split up. Part of it pushes the sled into the slope, that's what holds it there, and the other part is trying to pull the sled down the slope, parallel to the hill. And finally, fighting against that downward pull, we have the father's force, pulling up the slope. And here, this is the punchline. Look closely at the lengths of those arrows. The source material points out that the vector for the father's pull is longer. It has a greater magnitude than the vector for the force that's pulling the sled back down. That difference in magnitude is everything. It's the reason they move forward. If his arrow were even a little bit shorter, they'd start sliding backward, no matter how hard he tried.
So, after all that, what's the big idea here? Why do these arrows and brackets and magnitudes even matter? Let's boil it all down to the key takeaways.
So when it comes right down to it, a vector is really just an instruction for motion. It's defined by two simple things, its magnitude or its size and its direction.
And when we understand that a vector is a journey, not a destination, we get this incredibly powerful tool for modeling all the complex pushes and pulls that shape our world, from gravity all the way to the wind.
So I'll just leave you with this final thought. Now that you have this new lens for looking at the world, I want you to look around. I mean, whether it's kicking a soccer ball, watching the weather report, or just feeling the weight of the phone in your hand, where else are these invisible instructions shaping everything around you?